We are obsessed with autonomy. The dream is an agent that takes a vague instruction, figures it out, and executes the job while you sleep. But here is the reality check. In a sandbox, an agent that hallucinates is funny. In production, it's a liability. If your code structure is a straight line, reasoning directly to execution, you have built a fragile system. If the LLM misinterprets a prompt and decides to delete a database or refund the wrong user, that linear code will execute that mistake faster than you can blink. To build real systems, we need to break this line. So how do we stop a runaway train? We use the checkpoint pattern. Think of this like a save point in a video game. To interrupt a program effectively, you have to save its soul. We need to serialize the entire state of the agent, its memory, its variables, and its current position in the graph, and to write that to a database. This allows the graph to effectively go to sleep while it waits for a human signal and wake up exactly where it left off without losing any context. This is the architecture that we are building today. Now beginners solve this by writing a Python while loop with a confusing input statement that hangs the server. We are not going to do that. We are going to engineer the graph itself to recognize a sensitive node. The graph will execute the reasoning, hit our defined boundary, persist its state to memory, and then terminate the process. It only resumes when we inject an approval signal, loading that saved state and crossing the bridge to execution. Okay, let's now start building. First open our terminal and create a new folder, and after that, move into it. Now we are creating a fresh environment for this agent. Let's also activate the virtual environment. We need a few dependencies. We need LangGraph for the orchestration and LangChain OpenAI for the reasoning engine. We also install python.env to manage our API keys. Never hard code credentials. Isolate your dependencies. Let's install those. After the dependencies have been installed, we need to create our main.py file. Here we start with our imports. We need operator. I will explain why in a moment. And we need MemorySaver from LangGraph checkpoints. This is our database connector that allows the graph to pause and resume. Finally, let's load our environment variables immediately. To do that, we need to create a new file called .env. Here, we paste the OpenAI API key variable, and you should set this to your own API key. Now we model the brain. We create a class called agentState. We use type_dict to enforce a schema. Look closely at the messages key. We use annotated with operator.add. In standard Python, assigning a value usually overrides it. In LangGraph, this operator tells the state machine to append new messages to the existing list. This ensures our agent remembers the full conversation history even after we interrupt it. We will split our agent into two distinct phases. First, the reasoning phase. We initialize our LLM. I'm using GPT-4o with temperature 0 for maximum determinism. The reason step function simply takes the state, asks the LLM what to do, and returns the response. Note that we turn a dictionary. This updates our agent state automatically. Next is the action phase. In a real production system, this is where you hit the Stripe API, execute a SQL query, or send an email. For this demo, we will simulate a sensitive money transfer. We separate this into its own node so we can place a guardrail in front of it. If this logic was inside the reasoning node, we couldn't stop it. Now we build the architecture. We instantiate the state graph. We add our two nodes, reason and action. We define the flow. Start at reason, then move to action, and then end. This is the happy path. The path the code wants to take if we don't stop it. Now, the next part is the most important part of the video. We initialize MemorySaver to act as our persistence layer. When we compile the graph, we pass two arguments. First, the checkpointer. Second, interrupt before action. This specific command tells the executor, run the reasoning node, calculate the next step, but don't enter the action node. Freeze the state and wait. To use persistence, we need a session ID. In LangGraph, this is called a threat ID. This allows the system to distinguish between user A and user B. We wrap this in a config dictionary. We then define our initial user input, a request to transfer money. Finally, we handle the runtime execution. I will print a start banner so we can see clearly where we are in the logs. We start the graph by calling graph.stream. We pass in our initial input and the threat thread config. This kicks off the process. Now watch closely. This loop will execute the reasoning node, print that it finished, and then the script will pause. It will not print action. Why? Because our interrupt before caught it. To simulate the human in the loop, I'll use a basic Python input prompt. In a real app, this would be your API waiting for a front-end request. We check if the user typed Y. If they did, we need to resume. Here is the critical syntax. We call graph.stream again, but this time we pass none as the input. We pass the same thread config. This combination none plus an existing thread ID is the signal to LangGraph. It says, I have no new data, just wake up the thread and continue from the checkpoint. The graph sees it was paused right before action, so it releases the break and executes the transfer. Let's now see everything in action. Let's open our terminal and type python main.py. This will execute our node. As you can see, the reasoning node is running. And the process paused, waiting for our approval. Let's approve the transfer. And as you can see, then it resumed the execution and the action node completed the task. Let's look at what we just engineered. We didn't just write a script, we built a state machine. We used persistence to externalize the agent's memory so it survives process termination. We implemented interrupt logic to create a hard gate before sensitive actions. And we also used thread IDs to ensure that when we approve an action, we are resuming the correct user session. You now have a system that is autonomous when safe and obedient when necessary. This is just the foundation. We have moved beyond simple scripts into stateful architecture, but there are deeper patterns to master if you want to ship reliable agents to production. We are building the full stack here, one concept, one system at a time. We don't do hype, we do architecture. If you want to write code that actually works in production, hit subscribe. I'll see you in the next video.